everyone. So pull out your section 4.2 on division. If you don't have these, let me know. I'm pretty sure I emailed them to the people that weren't in class, but if you don't have this, let me know and I'll shoot you an email with it. But what I want to note first is our next exam. So our exam is going to be on Module 2, Test 2, on, I should not say module, wrong class. It will be on the Bayes systems, Venn diagrams, and addition and subtraction. Okay, and that's going to be on Tuesday, April 14th. And I understand that the president of the college extended those days, but we're using it to take a test. If we don't, we will get behind because we lost a Thursday before all this started. So that's going to be our test day, so we don't lose another day of class. So please read the directions on this week's So Wow, because you're going to have some things to do for 10 points. You're going to Zoom room me, and we're going to make sure you understand from here on out how to scan your papers with your phone and upload it as a PDF and email it to me. And I'm going to have a separate video that shows you how to do that. So that shouldn't be anything a big deal at all. And you do need to Zoom room me because by policy on our campus, our tests for the math department have to be proctored. And so we're going to proctor it using Zoom. Right, so just read the directions carefully, and then you'll know when I'll be available on Zoom at very specific times so that you can get on and I can be assured that you guys know how to use the scanner on your phones. All right, so we won't get everything in. We have to get everything up into this done, and then I'm going to make a separate video for determining if a number is prime, and you'll have to watch it at some point over break. Right? So, go ahead and read these 4 division problems. I mean, they're clearly division. And as you read them, I want you to write in the margin whether it's discrete data or continuous data that they're dealing with. So you can pause the video and then read them and come back in. All right. So when we're talking about Apple computers, we're talking about discrete data. We're not going to talk about 2.1 computers. That doesn't make any sense. When we're talking about ounces of juice, that's continuous. When we're talking about yards, that's also continuous. And then when we're talking about apples, really, now keep in mind we're dealing with elementary school. That's a discrete concept. When we talk about number of apples that go in an apple pie. All right, so these types of division questions can be divided up into 2 very specific types of problems. And you do have to be able to recognize them. On the final, we typically have write your own partitioning model for division, or write your own division model representing the repeated subtraction. So we really need to have a hold on how to recognize. All right, for problem number 1, that is what is called the partitioning model for division. And with the partitioning model for division, you have a preset number of groups or partitions that have to be filled. So in this case, you have the 4 5th grade classes, and you're going to fill them with these 24 Apple computers, right? So the partitions would be the 4 5th grade classes. I have a book, and I usually share it with everyone, but of course all this stuff is in my office. It's called When the Doorbell Rang, and it's a book, a children's book by Pat Hitchinson, and I'll kind of describe it a little bit. It's the most beautiful illustrated books, and that's why I used to read it to my kids, because the pictures were so cute. But it was a really nice example of the partitioning model for division. So in this book, you can see that the mom is making cookies, and she has a dozen cookies, and Sam and Hannah are the 2 kids in the book, and the mom says you have to divide them equally among the 2 of you. And so you see them physically pull plates out of the cupboard and I'm going to do this really lightly, they'll put 2 plates down to start off with, and then you can see them saying, grading the cookies, you get 1, 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 right? And they divide them equally among the 2 plates or the partitions. And then the doorbell rings. And then in comes someone else. In comes a neighbor kid. And the mom goes, oh, I'm sorry, you have to divide them equally amongst yourselves. And so you see the kids get another plate out. They dump the cookies back on the cookie sheet. And then they take the dozen cookies, right, and say, you get 1, you get 1, you get 1. You get 1, you get 1. And then, I should mention, and then they look inside the plate to see what the quotient is, what the answer would be to the division problem if we said 12 divided by 3. So the answer is found by looking inside the partition. And then the doorbell rings. And in walks another kid. And so now they have 4 plates. And the mom says, divide them equally. So they have the 12. And you get 1, you get 1, you get 1, right? Oh, we still have more to give. You get 1, you get 1, you get 1, you get 1. Oh, we still have more to give, right? And then when they're all gone, they look inside the plate and go, oh, we get 3 each, right? So you have to look inside the partition. And then you'll never guess, the doorbell rings again. And then they get out the 6 plates, and you can see them putting these plates down on the table. And the mom says, you've got to share them equally amongst yourselves. And so they dump them back on the cookie sheet, and they say, you get 1, 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 you get 1. And they look on the cookie sheet, and they're like, oh, there's more. And then they share them again. And then they have to look inside the plate and go, oh, we get 2 cookies each. And then the doorbell rings. I'm not joking. If I were Sam and Hannah, this would be the end, right? And then 6 kids walk in, and so they all have plates, and the expressions on Sam's face look so sad. And then the doorbell rings again, not to ruin the storybook for you, but the doorbell rings again, and Sam looks terrified, and then in walks the grandmother with this huge plate of cookies, and everyone's happy. I spoiled it for you, I know, but it was a really good example of the partitioning model, where they put the plates down on the table, and then they looked inside the plate after they divvied them up to figure out what the division answer would be, right? So it's a predetermined plate. Now, it doesn't have to be a plate. It could be a classroom building, right? Or it could be people, as in number 3. So number 3 is also a partitioning model. And the partitions would be Joey, Luke, Gracie, and Pam, right? So you get 1, you get 1, you get 1, you get a yard. Oh, we still have more yards left. You get a yard, you get a yard, you get a yard, you get a yard. Oh, we still have more yards left. And then after they divide them up, then how many yards each person is holding, that's the answer to your division problem. It's very, very different than the repeated subtraction model. All right? So the repeated subtraction model is like I have problem number 4. All right, so it says Carlos has 24 apples with which to make pies. It takes 4 apples per pie. So how many pies can he bake? Do you see we don't put the pie plates down ahead of time? We don't do that. We say, okay, we've got 24 apples. Let's scoop up 4 apples, and then we can put them in a pie plate and say that's 1 apple pie. And then we look over and we're like, oh, we got more apples. We can make more pies. So then we scoop up a big chunk of 4 and then put them in another pie plate. And then we look over and we're like, oh, well, dude, we can make some more pies. So do you see, you're repeatedly taking this big chunk out and then putting down a pie plate. And then at the end, you don't count the number of apples in the pie plate, like for this guy. You count the number of pie plates. It's so different, and it's so different the way you teach it. All right, so the other one, let's look at problem number 2, which is also repeated subtraction. All right, so it says Jeannie is making popsicles. She's got 24 ounces of juice, and each popsicle takes 4 ounces. So how many popsicles can she make? So it's not partitioning. She doesn't know how many molds to put out. So she has her jug, and she pours 4 ounces and goes, oh, I made 1 popsicle. And then she says, oh, but I've got more juice. So then she pours it into another mold and says, oh, now I've made 2 popsicles, but I have more juice. So she pours these chunks of 4 ounces out, And at the end, when she's out of it, then she counts the number of molds that she's poured it into. Do you see? It's very different from the partitioning where you already know how many molds to put out. It's not that bad. I know it sounds kind of confusing, but it's really easy, and we'll practice it. We'll practice it some more. I promise. All right, but that's one thing you have to know. So you've got to know discrete and continuous, and you've got to know the difference between partitioning and repeated subtraction. You probably didn't realize that there's these different types of problems. It's kind of interesting. All right, so some words that you've got to know, because these are the words that your kids are going to know. You need to know dividend, and dividend is that big number that you're starting with that you're going to divide up into pieces. The divisor is the number that you're saying, okay, in this case, I have 24. How many groups of 24 can I get out of? Or, I'm sorry, how many groups of 4 can I get out of 24? So that group maker is the divisor. And then the solution to a division property is the quotient. So dividend is what you start with. Divisor is the number of groups you're dividing it into. And 6 is going to be your quotient. And the one big thing, and we'll talk about this in Engage in New York, it's called the missing factor model. A lot of times, we'll go 24 divided by 4 equals 6, and is true. Do you guys, I remember doing this. I'm going to write it out like this. 24 divided by 4 equals 6 is true if and only if 6 times 4 equals 24. Do you see, did you guys learn it that way? I remember learning it that way. So if this problem was given, kids are taught what times 4 gives you 24. They treat it as a missing factor. You remember the factors are two numbers that are multiplied together. So what times 4 gives you 24? So they treat it as a multiplication problem. But I just wanted to mention that this missing factor problem, when I was looking at Engage, they use it to justify why 4 divided by 0 is undefined. So if you set that up as a division problem, it would be what times 0 equals 4, and you can't multiply anything by 0 to get 4. So that is why that does not exist, right? I learned it. It spells no. If you have a number on the top and a 0 on the bottom, then it's no. You can't do it. It can't be done. It does not exist. So I don't know. I just thought I'd throw that out there. I was looking at Engage New York, and that was an interesting way to teach kids why that is an undefined concept. All right. So the number line model. Number line model is really a repeated subtraction. So one way that they teach kids this is they say how many groups of 5 or how many chunks of 5 can be found in 15. So if you were on a number line, right, here's one chunk. Here's another chunk. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Here's another chunk. So that's why 15 divided by 5 is equal to 3. Okay? So how many groups of 5 can be found in 15? Now, if you teach kids this concept, if that's what division means, then dividing by fractions would be pretty easy to do. And of course, my manipulatives for us all, that we were all going to have a set of these to play with, are in my office. So I just really quickly made something to illustrate how to do 1/2 divided by 1/4. Because you're going to say, how many groups of 1/4 can be found in 1/2? Like if this made sense to you, how many groups of 5 can be found in 15, then this should make sense. How many groups of 1/4 can be found in 1/2? So I just picked up an index card and said, this is my 1. Okay? And then I divided it into 2 equal, I cut it up. Okay? I cut it up. So there's my 2 equal parts. Look at it that way. So each of those would be 1/2. Okay? Then I take my index card And you see I cut it up into fourths. So these are what my fourths would look like. Hope that makes sense, okay? So how many 1/4 can be found in 1/2? So a kid, and I just so that you can see it separated. Well, there's 1/4, and there's another 1/4. Do you see that? I just wanted to color it in so you guys could see that there's two of them all together. So how many 1/4 can be found in 1/2? The answer is 2. And there's some really nice fraction circles that kids play with that illustrate that. So they can figure out division with fractions without even knowing the crazy division rule where you change it to multiplication and reciprocate. That doesn't make a lot of sense to kids, but this does, because they're taught that division is taking a whole and figuring out how many of these pieces can be found in that whole. So it's a really neat concept if kids are kind of started off that way. So how many groups of 1/4 can be found in 1/2? 2. The answer is 2. And we did division without actually knowing any rules for division for fractions. It's a neat concept. All right, but we'll hit that when we hit the chapter in fractions. All right, so there's not a lot of properties. There's not a commutative property. 15 divided by 3 does not equal 3 divided by 15. So there's no commutative, no associative. Some people will say that there is identity property because 15 divided by 1 is equal to 15. So some people will say that that is an identity. Other people say that because it's not commutative and both directions don't work, it really doesn't. It's really not an identity. This book says that we've got 1 as a possible identity property. The closure property, well, you can see division is not closed. It is not closed under the whole numbers. Or integers. If you take two integers and divide them, you're not guaranteed to get an integer, right? So we talk about closure. That means if you start in a number set and you perform that operation, if it's closed, you'll end up back in that number set. So division's really not closed under anything except the rational numbers, and we'll get into rationals when we talk about fractions. And then the division by 0, right? Like what we said upstairs, a number divided by 0 is undefined. But I'll just say 0 divided by number always is 0. And I found this on Engaged New York. I thought it was kind of cool how they taught with decimals. So this is how many groups of 1 can be found in 5. And they told the kids what the dividend was, what the divisor was, and what the quotient was. So how many groups of 1 can be found in 5? Well, 5 groups of 1. But this is what's interesting. So how many groups of 0.1 or a tenth can be found in 5? So I'm hoping the whole lesson was talking about why this answer gets bigger. And it should make sense that we have a lot more tenths in 5 than whole ones in 5. So the lesson kind of went on, but I just wanted to show you that it was neat to show the kids that why, when you're dividing by a super small number, the quotient's really big, and it's because of the groups. But I also wanted to show you that, right, they need to know dividend, divisor, and quotient. But we'll get into this more again when we talk about decimals. We haven't got in there yet, but I wanted to just show you at least the words that these kids are using. All right, so let's actually play with some algorithms, okay? Let's do some algorithms. So it says, solve the 2 division problems as though you don't know any algorithms. We can use manipulatives, you can draw diagrams, or just think about it, but you don't know how to divide. you have no clue how to divide, you don't even know the operation exists, you're truly a fourth grader asked to solve these two questions. So this is where we would pause the video, and this is where I would walk around the room and see how you guys would attack this. Really, you might just want to pause it, give it a pause, and then see if you can at least come up with one way of doing these without doing the division algorithm. Okay? So go ahead and try them, then tune back in, and we'll mess with them together. All right, so I'm going to do a first about Warren. He's having 252 guests coming to his wedding, and each guest holds 4 tables. So how many tables? And I don't know division. Okay, so I thought, well, a diagram might be good for this. So we're going to have number of tables, right, and then number of guests for those tables. All right, so let's just say we have 50 tables. So we can hold 4 guests for each table. So that's going to give us 200 tables, or 200 guests. So I need more tables, right? So maybe we'll go up to 60 tables. So 4 times 60 is 240 guests. So we're getting there, right? We're getting there. Let's try, I don't know. I don't think if we went up to, I'm hoping you'd see if we went up to 70, we would have too many. So at this point, maybe we could just rationalize it out. So we need 252 guests. We're up to having 240. So it looks like we're 12 guests shy. 12 guests are going to be standing. So that means we need 3 more tables. So if we have 63 tables, 4 times 63, let's check it. There's your 252. So that was just drawing a table, right? Just using a table, kind of guess, check, and revise, right? So that's one way that we could do division, right? Is just using this. This is really repeated subtraction, right? Like you're taking 4 guests. We didn't know how many tables there were, but we're saying, okay, you 4 go over there. You 4 go over there. And I'm repeatedly taking 4 guests out of the 252, right? I did it in big chunks until you didn't have any guests left standing. So that's one way to do it. The other way you can do it is with this partitioning model, okay? So he has 252 piles. He wants to divide equally into 4 piles. So here are my piles. 1, 2, 3, 4 piles. And I'm going to draw manipulatives out, all right? So here we go. Let's draw these out. I have my 1s, my 10s, and my 100s. So I have 2 flats, 5 longs, and 2 singles. I'll give you a chance to catch up a little bit. Okay. So can I give everyone a flat? Do you divide them up equally? No. I can't give 2 flats and these 2 not have anything. So let's break them apart. So we're in base 10. So if I break out this flat, that's going to give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 longs. And then if I break this guy apart, same thing. 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we divvy them up. I mean, we divvy them up. So, I mean, most kids would say, you get that one, you get that one, you get that one, and you get that one. And then they just keep repeating until they don't have enough to share. For time's sake, instead of like going, you come here, you come here, you come here, and you come here. Okay, we still have more, right? I'm just going to say, okay, I'm going to take out a chunk of 4, right, rather than do that. 1, 2, 3, 4. There's enough for everyone to get 1. But usually they say, you get 1, you get 1, you get 1, you get 1, right? And they just keep crossing them off one at a time. But we know that if I take 4, everybody gets 1, right? 1, 2, 3, 4. 1, 2, 3, 4. Everybody gets 1. Okay, 1, 2, 3, 4. Everybody gets 1. And 1, 2, 3, 4. Everybody gets 1. Okay? So I have 1 long left over. I'm going to put it here, break it apart. 5, 6, 7, 8, 9, 10. Okay. So, I mean, if we were practicing this in 5th grade, right, this is what we would do. Okay, there's more to share. You get 1, you get 1, you get 1, and you get 1. Oh, there's more to share. And you need at least 4 to share, otherwise you have a remainder. You get 1, you get 1, you get 1, you get 1. Okay. And now to get the answer to the partitioning, you look inside the partition. So it would be 6 longs and 3 singles. So how many marbles are in each pile? 63. Right? So we just did division without dividing, with no algorithm. So guess what? Now we get to do it in a different base system. Okay? So this says solve using manipulatives. So the manipulatives are the flats, longs, and singles. And if we're going to solve it with manipulatives, we're going to do the partitioning model. Okay, so this tells us the number of partitions. Your divisor tells you the number of partitions. So we're going to take 33 and we're going to divide it into 2 partitions. Alright, so take your time. I'll give you a second to catch up with that and draw out your 33. So we have 3 10s and 3 singles. So it looks like everyone can get a 10, right? You get 1 and you get 1. And I can't do anything with this guy, so I'm going to break it apart. Now we're in base 5, so this has 5 singles in it. Okay, so now you each get 1. You each get 1. You each get 1. And you each get 1. So 33 broken up into 2 equal parts equals 14. Yeah, we divided using the partitioning model. Okay, so now you be careful. This is where you might make a mistake. When it says 11, don't think we have to make 11 circles. We're in base 5. So 1 long, 1 single, and 11 is this many fingers. 1 long, 1 single. Do you see that? So this is how many circles we have to draw, or how many partitions. We're going to draw 11, but 11 in base 5 looks like that. So it's not as terrible as you think it's going to be. So take your time. Let's draw out the manipulatives. Okay, I'm going to draw mine, you draw yours, and I'll give you a pause in case you need to catch up. Okay. Oh, I should do 400s. Okay, there we go. Sorry about that. All right, now we can pause. Now I'm going to pause. So we've got 400s, 2 10s, and 4 singles. All right, you ready? So I'm going to cross you off, and then I'm going to make, oh, because we've got 4, and so we can't share them equally. Oh, we're going to make a lot of longs. So there's 5 for you, 5 for you. Sneak over here and do some. 1, 2, 3, 4, 5 for you, and 2, 3, 4, 5 for you. Okay, so here we go. So I'm just going to use the, if I see 6, then everyone gets 1. So here's 6. So you get 1, 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 you get 1. 1, 2, 3, 4, 5, 6. So here's 6 right here. So everybody gets 1. 1, 2, 3, 4, 5, 6. Everybody gets 1. All right, so it looks like I have 4 left. So I'll cross off 1, and then I'm going to make 5 singles because we're in base 5. Cross off another one. 1, 2, 3, 4, 5. Cross off another one. 2, 3, 4, 5. Cross off another one. 2, 3, 4, 5. Okay. So now divvy them up. Like every time you see 6, everybody gets 1. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. There you go. So what is 424 divided by 11 in base 5? You look inside the partition. So it looks like it's 3 longs, 4 singles. So 3 longs, 4 singles is 34. All right. So let's play with one of the algorithms, like the traditional one, the division algorithm. So in order to divide, you need to know how to multiply. So I'm pulling out my handy dandy base 5, and we're going to set this up like a division problem. The only thing you could possibly make a mistake on is you're going to forget that you're in base 5 when you subtract. That's the key. So just like normal division, this is how I was taught. What times 2 equals 3 without going over? So 1 times 2 is 2, right? And then you subtract. So 3 minus 2 in base 5 is 3, or 1, and bring down the 3, right? And bring down that 3. So what times 2 gets you the closest to 13 without going over? So here's our 2's. Oh, it looks like we can get exactly 13, right? 2 times 4 is 13. So you'd put a 4 here. You would subtract the 13, and then you'd get 0. So that's how you can do it with the standard algorithm. Do you see that? Okay. You guys get to try it now. So, okay, something wonky happened with the printing. This should be moved up a little bit, and this something, yep, it got a little scrolled off, but that's okay. So these are right out of your book. So pause the video, and then the problem must be done in base 5. Ooh, there's probably going to be a remainder here, so we're not going to panic. It says represent the remainder as a fraction in lowest terms. Interesting. So we're going to think about fractions in base 5 already. I want you to do this one with with the formula, or standard algorithm, I should say. So do this one with standard algorithm. I mean, we could do it with partitioning as well. And then this one, partitioning. And remember, 13 doesn't mean 13 circles in base 5. I want you to really think about what 13 is in base 5, like how many fingers. So pause the video, try your best, and then turn it back on, and we'll see how you did. Okay? But try it, like really try it. My son said, I wonder how many people actually paused the video. I'm like, I don't know. I hope they do. So really try it, like pause it, flip back, look to see how we did the other two, and then come back and we'll see how you did. All right? So give it a pause. All right. Let's see how you did. So I'll come back and we'll do this one with partitioning, or with the partitioning model as well. But let's do the standard algorithm first. Okay. So what times 2 what times 4 gets you the closest to 2? So that would be 0. So we can't have a space there. So we're not going to fill in a number there. So we're going to go all the way over to 22. So what times 4 gets you the closest to 22 without going over? Oh, it looks like it's 3, because 4 times 3 is 22. All right, so we're going to put a 3 here. So 4 times 3 is 22, and then we subtract. And then we bring the 2 down. So what times 4 gets you the closest to 2 without going over? Well, that's going to be 0. So 0 times 4 is 0, and then we subtract, and then we bring the next number down. So what times 4 gets you the closest to 20 without going over? So it looks like 3 will be too big. I think 2 is where it's at. 4 times 2 is 13. All right, now be careful. 4 times 2 is 13, but remember we're in base 5. So when we go like this and make a 10 in base 5, that's how many fingers are in 10 in base 5. That's where you're going to make a mistake. So 10 minus 3 is 2 in base 5. And then we'll bring it down. Okay, and then what times 4 gets you the closest to 22 without going over? 3. So there's no remainder for this one, so the remainder must be in the other problem. Now, just for kicks, before we go on, if we had to do this with partitioning, okay, and we were going to divide this up into 4 partitions, just for kicks. So I want to just remind you, so we've got singles, longs, flats, cubes, and then what we called cubic longs. So I want to draw this out so you can see what it looks like. So we need 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So we'll have ones. We'll have tens. We'll have hundreds. We'll have thousands. And then we're going to have 10,000s. So let's start over here. So we have 2 singles. In base 5, if we stack 5 singles, then we have our tens, which we don't have any. And then if we stack the tens together, it makes the flats. And if we stack the flats together, it makes the cubes. So we have 2 cubes that are worth 1,000. So it goes singles, longs, flats, cubes. Do you see the cubes and the singles kind of look alike? So the tens and the 10,000s are going to look alike. So imagine stacking these cubes. They're going to look almost like a long. And there'll be 1, 2, 3. There'll be 5 cubes in each of these 2 cubic longs. But they recycle, like the pictures recycle. So the ones and the thousands kind of look like. These would, the tens and these 10,000s look alike. And then if we put these together, it's going to look like a flat, but a flat made up of these cubic longs is called a wall, right? And then it just kind of keeps going from there. I just wanted to show it to you. All right, so I cannot share these 2 cubic longs, so when we break them apart, they just are made into cubes. So we're going to have, a bunch of cubes. I'm going to make them littler. I don't think I'm going to have enough room. So we're going to have 5 cubes from this cubic long. I'll stick one more here. Okay, and then this guy is going to provide us with 5 cubes. So 1, 2, 3, 4. One more. I'll squeeze it right here. 5. Okay, so I can actually share those though, right? So I need, every time I see 4, everyone gets 1. So 1, 2, 3, 4. You get 1. You get 1. You get 1. And you get 1. And then 1, 2, 3, 4. You get 1. You get 1. You get 1. And you get 1. And it looks like I have enough, right, to share with the rest of the pile. So there's 4 more. Okay, so hundreds, I don't have enough to share. So we're going to have to break them apart and make them into these longs. We're in base 5, right? So that means we get 5 longs out of each flat. It looks like we can share those. Do y'all agree? It looks like we can share those. So I've got, you get 1, 2, 3, 4. Everyone gets 1. 1, 2, 3, 4. Everyone gets 1. And then I can't share these, so we're going to make them into singles. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then let's start sharing the love with these. So 1, 2, 3, 4. Everybody gets 1. 1, 2, 3, 4. Everybody gets 1. 1, 2, 3, 4. Everybody gets 1. And so then we look inside, right, the partitions to get the solution. So we have 3 cubes, no flats, 2 longs, and 3 singles. So there's my quotient. Is that what we got before? Yep. 3,023. Base 5. Right? So that's not so bad. I mean, it takes a little bit of time, but it's not terrible. Okay, so let's try this guy with the partitionings, and then I think I'll end the video. And then I'll make another one that you guys have to watch at some point between now and the end of break so that you can do the oh wow that I gave you. All right, so 1 long and 3 singles is 5 fingers. So we need 8 partitions. That's worth 5, that's worth 3, so we need 8. Okay. So here are our 8 partitions. And let's draw everything out. So we have our 1s, our 10s, our 100s, and our 1000s. So take your time. I'll wait for you. I'm going to draw my pictures. There's my cubes. Here are my flats, and here are my singles. Now this is the one where we're probably going to get a remainder because it said something about putting a remainder as a fraction in lowest terms. So we won't panic if we have some leftover ones. Okay, so I cannot share those cubes. So let's start breaking them apart and making them into flats. Oh, I don't think I left myself enough room again. I am not learning my lesson. 1, 2, 3, 4, 5. Goodness. We're going to squeeze them down here. 1, 2, 3, 4, 5. Okay, got them all in. All right, so I need 8 for everyone to get 1. So 1, 2, 3, 4, 5, 6, 7, 8. So everybody gets 1. One, 2, 3, 4, 5, 6, 7, 8. Okay, everyone gets 1 again. 1, 2, 3, 4, 5, 6, 7, 8. Cool, everybody gets 1. Okay, and then do you see this guy that's left over? He gets to become some longs, right? We'll cross him off, and then he gets to become some longs. But look, we don't have enough to share with everyone, so all those longs are going to become singles. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. A lot of arrows there. So we need 5 plus 3. We need 8 of something to be able to share. So here we go. 1, 2, 3, 4, 5, 6, 7, 8. Everybody gets 1. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Everybody gets 1. 1, 2, 3, 4, 5, 6, 7, 8. Everybody gets 1. And then we're going to have a remainder of 4. So let's set this up. You ready? So 3203 divided by 13. We're going to have 2 flats. So put it up above the flats. 0 longs, 3 singles with a remainder of, did you guys get a remainder of 4? Now they didn't want us to write it as a remainder. So I don't know if you guys remember here. I'm going to write it up, come up here. Do you guys remember how you did 25 divided by 4? There was 2 ways you were taught to write it, right? One like this, or 25 divided by 4 is 6, And then do you remember making a fraction out of that? So the quotient would be 6 1/4. So I think by the directions, that's what they want us to do. They don't want us to necessarily write it right like that. They wanted us to write it as 203 4/13. So good Lord, how are we supposed to reduce that? But remember, 13 is this is interesting. This, I haven't done this one, this many fingers. So you technically have 4 singles on the top, and if you're in base 10, 8 on the bottom. Oh, this is really cool. So it's really 203 1/2. All right, now I know we haven't talked about fractions yet, but if I asked you just on the side, if I said, hey everyone, what is 4/8? Reduce that down. I'm sure you would all say 1/2 without a hesitation. But that's what this technically is, because 13 in base 5 has 8 fingers. So this is what the answer is going to be on WebAssign. Oh, that's really interesting. It will be interesting when we do fractions. I promise it'll get easier. But woo, this is a long video, so we're going to cut it here. Now, I'm going to make another one that you have to watch between now and the end of break, because you've got some of divisibility rules on it, and they're super easy, so you don't have to worry. They're super easy. I'm going to post this one so you can get going on this stuff, and then I will post probably two shorter ones to finish this section and to do determining if a number is prime. So be on the lookout for those. I'll probably get those done tomorrow night and post those for you to watch at some point over break, so you can finish off the wow, and so we don't get behind. All right, have a good night, and I look forward to seeing you on Zoom over spring break. Talk to you soon.